2 courses. So normally this course will last for about 2.5 hours, not 1.5 hours. So if you have anything to do at 3 p.m., you can leave earlier because this class will be recorded. I think I am already started recording. Let me see. Yes, I'm already started recording. So if you have anything to do, okay, at 3 p.m., so do feel free to leave because I just want to help you as much as possible. So here I just summarize, I think some, I would say, confusing question where a lot of students did wrong in the past, and also some important concept which I think that will be greatly helpful for you to prepare the final examination. So basically, actually, it consists of these 5 parts. Okay, so especially for optics, because some students in that consultation session you mentioned to me that you still found the wave optics, which is still very difficult. Wave optics is still very difficult. So this is why I just collect the information from the student and find that the diffraction of light and the resolution of an optical system. So is what is confusing you most? So that I will talk about this part. Then I will also talk about some magnetics, especially help you to review the 5 right-hand rules we learned for magnetism. And then for quantum physics. Quantum physics, I think, is what you feel most headache. So that, but here, because it has 11 chapters, but out of this 11 chapters, as I said, okay, the most important 3 are this photoelectric effect, hydrogen atom, and quantum wave. So these are the most important 3 concepts out of the 11 chapters for quantum physics. 80% of the past examination paper are testing these 3. So I didn't say the other, 7 chapters is not important. It's less important as compared with these 3. But if you want to inform us, you should still take a look at that. So I don't think today I have time to go through tutorial 14 because here I already have a lot of examples. So tutorial 14 contains some other examples, for example, another part of quantum physics, such as quantum scattering, as well as how to say Heisenberg's uncertainty principle. Okay. Uncertainty principle. So that is solution was provided in the tutorial 14. So if you have time, so when you do the reversion, do also look at the tutorial 14. So because of tutorial 14, maybe I don't have time to go through it all, but you can take a look at yourself. Because I think even for this class, it will already take a lot of time. Okay, so first let's look at optics. As I said, for geometry optics, the most important thing is this multiple image system. So if you take a look, now it's the right time for you to take a look at the past examination papers, and you will be able to say the multiple image system are tested very often. Nearly every semester there will be about 1 question tested about multiple image system. So this is definitely everyone of you must understand for geometry optics. Okay. So that let me help you review the method we need to use to solve the multiple image system. Multiple image system is confusing because the image from the first step can be served as an object for the second image step. So some students are confusing, okay, whether the object or image in the intermediate step are real or not, are real or imaginary. But now what I would like to let you know, then you forget about this. You don't have to judge whether the image or object from the intermediate step, okay, is real or not. You just need to, follow my 3-step recurrence method. Okay, 3-step recurrence method. You can already get the results for the final image. And then you don't have to worry about what happens in all the steps between. So normally for multiple image system, what will be given to you is a focal length of every lens and the mirrors. Okay, every lenses and the mirrors. So which means Fn is given. So that depending on the question, it will also give you the location of the object, which means P1 is given, or give you the location of the final image, which means Qn, maximum n is given. Okay. So that if this is the case, you just follow the step, follow this 3 steps, then you will be able to solve for the final image or the initial object. So for example, if the initial object P1 is given, what we do is start with step 1, apply the image equation for the first length. So because P1 is given, F1 is also given, as I say, every F will be given. So that in this equation, you can easily deduce Q1, the image distance in the first image step. Then here comes the most important part. Once P1 is given, once Q1 is obtained, we use Q1 to get P2. P2 is the object distance in the second image step. We use Q1 to get P2. So the procedure is P2 equal to D. D is the distance between the first length and the second length. Okay, minus Q1. Yes? Any question? So let me repeat. Okay, P2, the second object distance is equal to D12, the distance between length 1 and length 2, minus Q1. Once P2 is obtained, and then you redo 1, okay, redo 1, update n equal to 2, so P1 divided by P2 plus 1 divided by Q2 equal to 1 divided by F2, then you will be able to get Q2. Once Q2 is obtained, we use Q2 to deduce P3. So the P3 is just equal to the distance between length 2 and length 3 minus Q2. So always this procedure, and then you can't forget about what are the object or image in the intermediate step. You directly follow the method here. You can get to the end. Okay. So always apply this procedure. Okay. Always apply this procedure. So now I will have 2 examples to show you how to apply this kind of method. So the first one is a question test about 4 years ago. Here we have an optical system comprising a diverging lens. This is a diverging lens. And a convex mirror. So this convex mirror has of course they are separated by 20 centimeters. An object is located at 10 centimeters to the lens. Okay, because the whole distance here is 20 centimeters. So that this object is 10 centimeters to the lens, also 10 centimeters to the mirror. The mirror has a radius of curvature equal to 20 centimeters. While the length is focal length is minus 20 centimeters. Okay, if this object only emit to the right, so that it will be imaged by the mirror first, and then the reflected light will go through the lens to form a second image. So that the question wants you to determine the final image formed by the lens, its orientation, magnification, and location. Okay. Clear about what this question asks for? Take a look. So that my object is located at this position. Okay, it emits to the right. First the image by the mirror, then the lens. Want you to look at the final image. Now, before I start to show how to apply my 3-step recurrence method, let me first ask you a question. This is a convex mirror. Okay, a convex mirror. So that its radius of curvature equal to 20 centimeters. What's the corresponding focal length? First, it should be positive or negative. For convex mirror, it should be positive or negative. Very good. Look at the shape. A convex mirror, its focal length should be negative. The magnitude of the focal length is R divided by 2. Okay, is only R divided by 2. So that for the first image step, you should be able to comment, okay, my F1 is minus R divided by 2. Minus R divided by 2. So in this case, is minus 10 centimeters. So that the question said that the object is located 10 centimeters to the lens, also it's 10 centimeters to the mirror. So that my P1 is 10. Right, P1 is 10. So F1 and P1 is given. I apply the first image equation 1 divided by P1 plus 1 divided by Q1 equal to 1 divided by F1. So that this can quickly give us Q1 equal to minus 5. minus 5 centimeter, with a corresponding magnification equal to minus Q1 divided by P1, which is 1 divided by 2. Okay. So then, as I said, intermediate step, you just keep the value of Q1. Don't have to worry about whether it's real or virtual, and on which side of the mirror or lens it is located. Okay, you just keep its value. Then use Q1 to get P1. The idea is to use the idea. Oh, sorry. This should be Q1. Yes, this here should be Q1. So that for the second image, in order to find out its object distance, my P2 should equal to D, the distance between the lens and the mirror, minus Q1. So which is now 20 minus 5. Okay, then it becomes 25 centimeter. So my P2 equal to 25 centimeter. Okay, exactly follow my procedure. Step 2, and then F2 is equal to minus 20, given by the question. So that I just substitute the F2 and the P2 into this equation. I can get my Q2 is minus 11.11 centimeter with a corresponding magnification equal to 0.44. So in this case, the total magnification equal to M1 times M2. So now it's 0.22. Then this comes so this is all the math. But the question also wants us to comment on the final images property, whether it's real, virtual, upright, or inverted. So first, as I said, for the images property, whether it's real or virtual, only depends on the sign of the last image distance, which is only depending on the sign of Q2. Q2 equal to minus 11.11. This means this is a virtual or real image. Yes, very good. We look at the final image distance. It's negative, so that it should be a virtual image. Okay. Then whether it's upright or inverted, you have to look at the total magnification. The total magnification is positive, which means it's upright or inverted. Very good, upright. Total magnification larger than 0, which means upright. Smaller than 0 is inverted. So this is an upright image, okay? Upright image. Total magnification equal to 0.22. So here you have to bear in mind, okay? Now it's a virtual image. Virtual image should appear at the sun side where light is incident. So that we learned for the lens, if light coming from the left, virtual image should appear on the left. But now, because the light is, reverted by mirror, so now the light is coming from the right. Light is coming from the right. For a virtual image, in this case, a virtual image happens on the same side of the direction where light is coming from, so that my virtual image should be located on the right of the lens. Okay, to reverse the sign convention. As I said, for the lens and the mirror, image by lens and the mirror, the sign conversion, the table, okay, in my tutorial slides is what you have to remember, okay? Remember that that slides, otherwise you will not be able to comment on the property of the mirror. I think the image, okay? So take a look at my summary slides. Any question here? So this is the answer you should provide for this answer, or for this question. Okay. Now then, let's look at another one. So about 5 years ago in spatial term. So here in this figure below, we have a candle. We have a candle placed at the center of curvature C of this concave mirror. So center of curvature, what does that mean? So which means its object distance to the mirror is how much? How many of the focal distance? Yes, very good. It should be twice of the focal distance. Very good. Because for the mirror, the radius of curvature is twice of the focal length. So that if something is placed at the center of curvature, so which means the corresponding object distance is just twice of the focal length. Okay. So it says the focal length of the concave mirror is 10 centimeters, which means now my candle should be placed, to this mirror in 20 centimeters. Okay. My candle should now place in 20 centimeters to the mirror. Okay. Apart from this mirror, we also have another converging lens, whose focal length is 25 centimeters. Now its distance to the candle is 65 centimeters, as plotted in this figure. Okay, so that the candle is placed at the center of curvature, which means its distance to the mirror is 20. So its distance to the lens is 65. This is what this question tells us. Okay, the candle is viewed by looking through the lens from the right, so that as the student sees two images of the candle, not just one. Two images of the candle. The question also tells us that the first image is formed by light directly passing through the lens, while the second image is formed by light that first go through, so which is light now emitted to the left. Okay, so that it will first be imaged by the mirror and then go through the lens, to form a second image. Okay, so the first one is formed by light emitted to the right, so directly imaged by the mirror or by the lens. The other is first by mirror, then an image formed by the lens. Okay, so the question wants us to determine the position of the first image with respect to the lens, and then want you to comment whether this is a real, virtual, upright, or inverted image. Also, we have to draw a ray diagram to show how the image is formed. The second part, of course, wants us to determine the position of the second image as well as its property. Okay, and finally draw a ray diagram. Okay, so this is what the question. This is what this question wants. Okay, so now let's look at 12 marking total, six, for each. So first, for the first image, as I said, directly go through the lens. That is okay. So I think every one of you should try to get a 4 mark for the first part. So that this one is directly formed by this lens. You can see the image distance P1 is already given. Focal length is also given. So that it only goes through the lens once. So that we just apply one image equation is okay. 1 divided by P plus 1 divided by Q equal to 1 divided by F. F and P are both given, so that you can calculate my Q is about 40 centimeters. Positive 40, which means this is a real or virtual image. Yes, very good. This is a real image. Okay, this is a real image. Its position is, of course, located 40 centimeters to the right, of this mirror. Okay, so of course it's a real image, inverted, because if you do minus Q divided by P, you get a negative value, so that is inverted. So that we draw the ray diagram. As I said, to draw the ray diagram, we normally use either 2 out of these 3 rays. The first ray is emitted by the top of the image. That is directly, passing through the center of the lens. For this ray, it will not change direction. It will directly go through. It will directly go straight through. The second ray is, emitted by this image, but parallel to the horizontal axis. Then the refracted ray on the transmission side will now passing through the focal length. Okay, or we have the ray emitted passing through the focal length. After refraction to the transmission side, it will be parallel to the horizontal axis. All 3 rays will converge at the same point, which is the position of the image. So that, as I said, you only use either 2 out of these 3 rays. Okay, here I draw 3. Just to show you, okay, you can use either two of them. Okay, you can use either two of them. So that for this one, three points for the image equation. 3 points for the 3 points for this ray diagram. Okay, for this ray diagram. Any question? So now let's look at the second part. Okay, for the second part, the image, then you have to apply my recurrence method because it's the object first the image by the mirror and then correspondingly in the following step it will be imaged by the lens again. So that the image was formed twice in this whole imaging process. So that we have to apply my recurrence method twice. So first, as I said, f1 equal to 10, p1 to this mirror, as I said, located at the center of curvature, which means this distance is 20. So p1 is 20. So in this case, you can get a q1 equal to 20 centimeters. So q1 equal to centimeters. This is actually real image, located at exactly the same position of the object, but it was inverted. Okay, the mirror is inverted. So this is the object. This is the image. So that in order to draw the real diagram of this image, what we do is, of course, here you use either two out of these 3 rays. The first ray emitted parallel to the mirror, it will be reflected back at the focal length. Okay, it will be reflected passing through the focal length. The other ray emitted passing through the focal length will be reflected parallel to the horizontal axis. Or the third ray that is emitted, to the center of the curvature, it will be reflected symmetrically. That is will be bisect by the horizontal axis. As I said, either these 3 rays will converge at the same point, which is the position of the image, using either 2 out of these 3 rays to get the image. Okay, to get the image equation. As I said, in this case, you find the image located exactly at the same position of the object, okay, but it was inverted. So that which means its distance P2 to the length is also 65 centimeters. So that this equation is exactly the same as this one, because f is 25. F is 20. In this case, yes, my f is 25. P is 65. Okay, so here this should be P. Okay, P is 25. To f2 is equal to 25, the same as the previous, the same as the previous case. So that we just substitute all the value inside. Then you can get what is my Q2. But now, because the image here is inverted, then it forms another real image which was inverted again. So that the second image here, it should be a real upright image. It's a real and upright image. Okay, so this is a very interesting story in this case, which means if we place a candle, okay, just at the center of the curvature of this mirror, and then if we have another lens, then at the other side we will to see image, mirror symmetry inverted from each other. So in this case, we have one object, first the image by the mirror, and then at the other side of the lens, we will see 2 opposite image, okay, opposite to each other. Okay, so you can do the experiment yourself if you have this, if you can borrow a lens and a mirror in the lab. Okay, so what you have to comment on here is the second image is located exactly at the same position of the first one, 40 centimeters to the right of the lens. It's a real upright image. Okay, any question? Okay, so if no question, yes.
One question. The final image, right? Can it act as an object for the mirror again?
Can you what?
Act as an object for the mirror again.
The object for the mirror. So the
the final image.
The final image, yes.
Can it act as an object for the mirror again?
Oh no. So let me repeat what his question is, because now we have the final image here, whether we can, look at we can view this as an object for the mirror, right? Whether it will be imaged by the mirror again. So the question is no. Why? Because this image is formed by light ray that is going to the right. For example, the light source, if it only emits to the right, then it will not be imaged by the mirror. Only for light ray that is emitted omnidirectionally, so that light ray first, or emit to the left, that can encounter the mirror. Once it forms back, the light ray will always go to the right. It will not encounter the mirror again, so that it's only for one image. Okay, it's only for one image. Okay, so it will not be imaged by the mirror again. Okay, just remember this one. Okay. So for the mirror, so no matter for which case, if we have a mirror, the mirror only for one image. So for lens, maybe my light ray, for example, going from the left first encounter the lens and then encounter the mirror. But the mirror always from one image. Once the light was reflected back by the mirror, it will not go through the mirror again. It can pass through the lens, the second times, but it will no longer be imaged by the mirror again. Okay? Good. So then the second part is the interference of light. Okay, so that for interference of light, normally, as I mentioned, what we should do is light, only two beams of light, as long as their frequency are the same and meet each other in the space, it will form bright or dark fringe. This is what we call interference. So whether it's bright or dark fringe, depending on the optical path difference between these two beams of light. If the optical path, so if R1 and R2 are the optical paths for V1 and V2, then if their difference equal to an integer times lambda, then at that position, we will get a bright fringe. If their difference equal to a half integer, n plus 1/2 times lambda, that will be dark fringe. So this is a very simple story. So that I told you normally for all case about 90 or even 95% test view interference for this table, because we only learned the Young's double slit and the thin film interference. So normally what we do is we should let the optical path difference equal to m times lambda for bright fringe, or m plus half lambda equal to for the dark fringe. So depending on whether the question asks for the bright or dark fringe, we just equal, one value in the second column here to this guy or this guy. So if it's bright fringe, we equal this either 3 out of this value equal to m times lambda. If it's dark fringe, equal either 3 of this equal to half m plus half lambda. So that allows for different experiments, what we have is the optical path difference is calculated in a different way. So for Young's double slit, the optical path difference is d times sine theta. Okay, optical path difference is d times sine theta. So that in the small angle approximation is d times y divided by the distance between the two slits and the screen. Okay, forming the bright and the dark fringe. Okay, so as you can see, if you equal this to this and this, you will be able to get what is my y. Okay, the position of the bright or dark fringe. Okay, so for thin film then depends on whether I have this the phase difference upon reflection on the sun or not. I have 2nt or 2nt plus lambda divided by 2. Then depending on our configuration, okay, we should use 2nt or 2nt plus lambda divided by 2. So as I said, if the film's reflective index is just between the two planes, the reflective index of the two planes, then we should use 2nt. But if the reflective index of the film is larger or smaller than both of the reflective index of the plane, then we should use 2nt plus lambda divided by 2. Okay, then we should use 2nt divided by lambda over 2. Okay, so now let's look at the experiment. Okay, for the thin film, the first one. Here we have an oil tanker spill a large amount of oil onto the sea surface. The oil film is 270 meters thick. The reflective index of this oil is 1.4 42. So this is a film. Then the refractive index of the water, seawater, is 1.33. Then view from above the oil. I want you to comment whether there is any visible wavelength that will be strongly reflected, or if there is any visible wavelength, there will be low reflection. Okay, so what do I mean by visible wavelength is 400 to 700 nanometer. Okay, 400 to 700 nanometer. So now clearly this is a thin film, thin film problem. So that my N2 is 1.42. Its refractive index is larger. N2 is larger than both N1 and N3. So that in this case, my delta L equal to how much? My delta L in this case, my optical path difference of this two rays should equal to 2NT or 2NT plus lambda over 2. Yes, very good. That should be 2NT plus lambda over 2 because one ray will have pi phase shift, one ray will does not have. Okay, so the way to judge whether we have this pi shift or not is to see whether the reflections happens in the low index or high index material. So at the first interface, reflection here happens for the low index material. We have pi phase shift. For N2 and N3 boundary, the reflection here happens in the high index material N2, so that it does not have any phase shift. Does not have any phase shift. Transmission will not cause any phase difference, so that it will still remain zero. So that my formula should be 2NT. So that for the first question, okay, first question, I want light to be strongly reflected, which means I'm looking for bright or dark fringe. Right. Yes, very good. Low reflection for the second part, bright or dark. Yes, very good. So which means what you have to do is to set this 2NT plus half lambda equal to an integer times lambda for the first question. The same optical path difference, the same value to a half integer m plus 1 over 2 times lambda. Okay, for the second part. So that let's look at the first part. So that we set 2NT plus half lambda equal to m times lambda. Quickly you can get, okay, my lambda is equal to 2 times n2t divided by an integer minus 0.5. Then we just check what happens because m can be any integer. We just check substitute different integer m from 1 to 3, okay, or even larger, and to say whether there is any wavelength that will fall in the visible wavelength range, okay, in the visible spectrum. So that we found that, okay, m equal to 1, so it's about 1,500 nanometers. That is in the infrared, okay, not in the visible frequency. So the m equal to 2 is about 500 nanometers, something like yellow or green light, okay, that frequency. So that this fall in the 400 and 700 nanometer visible spectrum range. Then M1 equal to 3, I have 300 nanometer. Okay, it's already in the ultraviolet below 400 nanometer. So that here we should comment that, okay, here we have one wavelength that will be strongly reflected. Its corresponding wavelength is this one. So that when you further increase M, it will of course make lambda smaller and smaller. So there is only one color within the visible spectrum that will be reflected strongly. Okay. So that for the second part, low reflection required dark fringe distracting interference. So that we have 2NT plus half lambda. This is okay, M2 plus half lambda. This half lambda cancel out each other. So this is why for the second part we end up with this equation. So now my lambda should equal to 2T divided by M2. So another integer. Then we check whether there is an integer that can make lambda, fall in the visible spectrum range. So when you check this M1, M2, and M3, for M1, it's 766 nanometer, still outside the visible. But when you suddenly change that from M2 from 1 to 2, then it's 383 nanometer. Okay. Already, fall below the lower bound of the visible spectrum. So this is also outside the visible spectrum. So which means in this case, we cannot have any wavelengths in the visible spectrum satisfy this equation. Because if we want to validate an integer that is between 1 and 2, which is of course impossible. So that in this case, we should comment there is no visible wavelength that will lead to low reflection. Okay? Any question? Any question here? So if no question, then let's continue. Okay. So this one, for this question, okay. Okay. So for this question, this is I would say a very difficult question. I would say a little bit abnormal because I said nearly 95% is testing thin film or double slit interference, where you can directly, write down what the output has different is. Either D comes and say that's a double slit, or 2NT or 2NT plus half lambda for thin film. So only for a very rare case, we have to calculate this data ourselves. But that does not necessarily that kind of question cannot appear. So this is a very good example, when such question was tested in the final examination. So normally that question was tested used to distinguish some good students, because normally it will not take a lot of mark. So normally 5 or 7, something like that. Okay. Then let's look at it now. But if you follow that procedure to find out what is denial, okay, you can still solve this question. Okay. So this is what we call noise mirror. I think in the LAMS video, Professor Song-Hu Yu already talked about the noise mirror. So I would say this will not be tested very often. So it's not as important as a thin film or the double slit, but it may also be tested sometimes. So it was tested, maybe that will be some difficult question. So what I would suggest, if you say such kind of question, where you can not directly apply the formula from the formula sheet, but have to analyze it a little bit, you put this question, in the end, when you solve all the other easy questions, and you solve this kind of question. Okay, now let's look at what this question talks about. They said, okay, I have a noise mirror in this in this case. Is the distance between, so where I have a light source placed 1.6 centimeters to a screen. Of course, the bright fringe is formed on the screen. Why there is a bright fringe formed on the screen is because here we have a mirror. Okay, here we have another mirror placed between the source and the screen, placed below the source and the screen, and the distance between the light source and this mirror is 1 centimeter. So that's because of the existence of the mirror, light, the interference pattern will be formed by light directly incident on the mirror and the light reflected from this mirror. Okay, because we have reflected light interfere with light was not reflected, so that we also have two light ray. So they will form a series of bright and dark fringe on the screen. Then it's observed that the 600th bright fringe occurs at point P, which is on the screen of the same height of the source. So which means that 600th bright fringe, its distance to the bottom is about 1 centimeters. Then in this case, I want you to calculate the wavelength of the light source. Okay. So now let's look at how to solve this question. So that we are looking at the bright fringe at point P. So first we need to understand this bright fringe is formed by light, directly emit parallel to the mirror without any reflection, arrive at point P. The second ray is reflected from the mirror and then arrive at the point P. Of course, you can say one goes straight trajectory, the other goes this curved one. Okay, this reflected one. So of course, their optical path is different. So it is said P is the same height at at the source. So which means for my ray 1, my optical path is directly this distance 1.6 centimeters. Then how about for ray 2? Ray2 is actually go this curved trajectory. In order to find the total length of this one, so which is we assume this is L1, this is L2. Clearly L1 and L2 are equal to each other, okay, upon reflection. So that's the way to do this is we assume, okay, there is a mirror downstairs. So that the mirror, there is a virtual image downstairs, okay, below here, below the mirror. So its distance from the mirror, of course, is 1 centimeters. Then we found out the distance from S prime to P, from S prime to P. So that is give us this right angle. So it's actually equal to square root. Now this edge become 2, this is 1.6, becomes square root 2 square plus 1.6 square. Okay, so this is R2. Now this comes the most important part. This is the physical path of the second ray. Is this physical path the optical path? No, very good. Why not? It will gain. This is very good. This, my question is, does this optical path equal to the physical path? Some of you shake your head. You said, okay, this is no. Why? This is because light can gain phase, pi phase difference upon reflection. So especially light reflected by ND mirror, that will gain a pi phase difference. So similar to V plus lambda over 2, on 20. So if light was reflected by a mirror, this always happens. No matter you place a mirror in water or in glass or in any kind of transparent material, especially in air, light reflected by the mirror will gain pi phase difference. You have to plus another lambda over 2 onto the physical path. So that in this case, my optical path should equal to the physical path S prime P plus lambda over 2. So that my R2 here should be about 2.5 centimeters plus lambda over 2. This is my real R2. Then R1 and R2 are given. Delta L equal to R1 minus R2. This is what I said. You have to calculate in this way. This is why it's difficult. Because now your delta L, you have to find out, on your own. You cannot directly apply to NT or d sine theta directly in the formula sheet. So now you have to find it out. So once we found this delta L, it is said, okay, this P is the 600 bright fringe, which means this delta L should be equal to how much? How much times lambda? Yeah, it just 600 times lambda. Okay, this M equal to 600. You directly say this delta L equal to 600 times lambda. Then this half lambda, put on the right hand side in the denominator, you can get, okay, my lambda is about 16 micrometer. 16 micrometer. Okay. So that's, as I said, the calculation. So if you forget to plus this half lambda, you will be deducted. So put a half lambda here, which is 2 mark. If you directly use R2 minus R1, then divided by 600, without minus this 0.5, you will be deducted 2 mark out of the 5. Okay. 2 mark out of the 5. Okay. Then if you correctly found out the optical path difference in this way, you already will be awarded 4 marks. So the last part is only 1 mark. Okay. Last part is only 1 mark. Okay. Set it to 600 is only 1 mark. This half lambda was 2 mark. Okay. Half lambda was 2 mark. Calculate R1 and S. This P1. That was this 1 mark. R2 equal to S prime P, this also worth 1 mark. Plus half lambda equal to another mark. And then the final one is the final mark. This is how the 5 mark will constitute. Yes, any question? Any question? Okay. No question. Let's continue to the resolution. Okay. The resolution. Okay, so for the resolution problem, so let me tell you again. Is because when we have a point source passing through any aperture, such as a lens or a mirror, even it's a point source, its image will not be an infinitely sharp point. So in this case, if the two objects, are very close to each other, and then the image, because the image is a hot spot, okay, will begin to overlap. Once it overlaps, we will not be able to resolve these two objects, these two images. So that's this is why for any optical system, we will say, okay, its resolution is limited by the refraction. Its resolution is limited by the reflection. So in this case, we just means for any optical system, the two objects cannot be located very close to each other, because if they are too close to each other, the image will be formed in this way, not well separated, will form in this way. So that for every image system, we will be able to have a smallest distance or the smallest angular resolution that we can resolve these two objects. Only when the distance or the angle theta or the distance between S1 and S2 are larger than a certain value, we will be able to resolve these two images. Otherwise, we will not. Okay, so that's for the resolution. If we have a slit aperture, such as a film, or a two-dimensional mirror, concave mirror, and then the minimum angular resolution is lambda over d. While for circular aperture, the minimum angular resolution is 1.22 times lambda over d. 1.22 times lambda over d. Okay, so this is the basic concept about the resolution. Now let's look at two questions related with the resolution. Here, consider two light sources with a wavelength 500 nanometers. So wavelength is given. It was placed to the left of a convex, so which is a converging lens, with a focal length equal to 10 centimeters, as shown in this figure. So given that their images are formed on a screen placed 11 centimeters in front of this lens, so this 11 should be what? My image or object distance. This 11. This is the image distance. Very good. This 11 is actually my image distance. Then I want you to determine the location of the light source L. L is actually the object distance. So this question is giving you focal length and the image distance. Try to find out the object distance. The first part, only the first part. Then it also tells you that, okay, this, because we have two light sources, and the image of this two light source just satisfy the just resolved condition. Then I want you to find out their corresponding separation. This distance d here, just resolve, which means this angle theta just equal to 1.22 times lambda over d. Why I say it's 1.22, not just lambda over d. Why I said it's 1.22? Why? So which means I'm considering circular aperture. Why this is a circular aperture, not a slit aperture? From the question. Sorry?
Convex.
Slit can also be convex, as long as it's not circular. Right? So you can say slit. No paper. Okay. So for if we call a slit aperture, okay, this is a concave mirror for a slit. Okay, circular, which means I have to circularly it around something. But why I said this is a circular aperture? From which part I can get such information?
Diameter.
Yes, very good. It tells you the diameter of that mirror. So if it's a slit, it will say the width of the convex lens. If it's width, okay, width. But for diameter, of course, it can be circular. Yes, very good. And also here I can highlight for you. Normally for the resolution, we will test you for circular aperture. The slit aperture, come, whether less often, less frequent. So normally it's a circular aperture. So remember to put this 1.22. Okay. So now this part first, use the image equation to find out the object distance, and then use the just resolved condition to find the theta m, and then find the corresponding d. So this is the idea. So of course, the first one, given Q and F, find out P. I get out my P is equal to 110 centimeters, which is very easy. Okay. And then for the second part, I am looking at the just resolved condition theta. Theta should be equal to 1.22 times lambda divided by d. And this theta, according to this graph, is also this distance between the two light sources divided by L. L is what we have already calculated. So that my D should just equal to 1.22 times lambda L divided by D. You substitute lambda, so L we already calculated, and the diameter of the lens into this equation. You will be able to say, okay, my distance is just 33.55 micrometers. Okay. Any question? So if you have any question, raise your hand and feel free to ask. Okay. Now let's look at another example. So actually, this is actually a deformation of our tutorial question. Okay, one of the tutorial question. I think what I would like to highlight for you for the resolution problem, you don't be afraid of such question. So normally it's actually to find out the smallest angular relation or the smallest distance between the two objects. So directly apply this 1.22 times lambda over d. So you can directly get the answer. Okay, so that here it says we have a moon nearest to the Earth's surface. The distance between the two surfaces, which means now the L is given by this number, kilometer. Okay, the moon is now viewed from the telescope. The wavelength of light used is 575 nanometer. Using this telescope, the smallest distance can be resolved between the 2 points is 1 centimeter. Okay, is 1 centimeter. Okay, so which means here I give you the resolution. The smallest distance, which means just the distance corresponding to the just resolved condition. Okay, just resolved condition. Then I want you to calculate the angular resolution of the telescope and the diameter of the mirror. Okay. So that give you the smallest distance, and then the smallest, the angular resolution should be just d divided by L. D divided by L. D is 1 kilometers, and then divided by the corresponding L given in the question. I find it's about 2.75 times 10 to the minus 6. This is in radian. Okay, not in degree. This is in radian. And in order to find the diameter of the telescope, as I said, for any resolution problem, theta equal to 1.22 times lambda over d will be definitely test. This is the formula you have to write down. Once you identify this question has this resolution, okay, the first thing is write down this formula. Okay, so even you didn't get the final answer, maybe you will be awarded 2 marks there. Okay, because it's the resolution. Then as you can see, theta is what we have already calculated. Lambda is given in the question. I think it is 575. Okay, 575. Then we can quickly calculate d. In this case, it's about 0.255 meter. Okay, quite straightforward, right? So now, yes, now we will look at some question that is more difficult. So this is also, also that. If the 2 previous questions was tested, I hope every one of you should try to get 4 marks in this one. So now this is a difficult one. I think many students will make some mistake there. I think even the examiner at that time also made a mistake with this question because his solution is wrong. So when I solved this question, I found, okay, this is not the right solution. Actually, the right solution actually go beyond of our course. Okay, so this is what I would like to let you know. Okay, let you know. For this question, okay, as I said, this is least important because I don't think it will be tested very frequent. Such questions is very difficult. As I said, it's not the previous two are normal question, so that may be tested. But this one is a very difficult one. As I said, the frequency of the difficult question to be tested is not very high. Okay. So here we have a single lens generates deflection pattern of bright and dark fringe on a screen located 2 meters away from the lens. Okay, so that its distance to lens is 2 meters. This L. So if the first and the second dark fringe, are separated by 0.1 millimeter in distance, I want you to determine the diameter of the lens. Again, diameter means it's a circular aperture. Okay, 1.2 times lambda over d. Then I said, given the wavelength of light, I want you to calculate what is the minimum distance that this lens can resolve. So it's the resolution power. Find out the theta minimum and then get what is the d minimum. Okay, what is d minimum? So that Now, first look at the right solution. Okay, the original solution provided by the examiner. Okay, so we assume, okay, we have a single slit. We have a single slit. For a single slit, when light passing through the slit, of course, it will form diffraction pattern, right? It will form diffraction pattern. While the position of the diffraction pattern is given by A times sine theta equal to M times lambda. So that for the first dark fringe, also dark fringe, okay, for the first dark fringe, we have A times the corresponding sine theta equal to lambda. For the second dark fringe, A times the corresponding theta should equal to 2 times lambda. Okay, as I said, sine theta is actually equal to y divided by L. So if we assume the y sine theta equal to y divided by L, if we assume the position of the first and the second dark fringe are y1 and y2 respectively, we will be able to rewrite this diffraction equation into this one. Then we use the second equation minus the first equation. You can get A, which is the width of the slit, times the difference between the y coordinate, then divided by this L equal to lambda. Then in this case, the question already gave us what delta y, so which means y2 minus y1 it is. It's about, I think, 0.1. Okay, it's 0.1 in millimeter. The question tells us 0.1 in millimeter. And also it gives the lambda and L. So that from this equation, we can quickly calculate the width of the slit. The width of the slit, right? Because y1 minus y2 is given, L and lambda is also given in the question. In this case, we can quickly calculate the width of the slit. That is the size of my aperture. Once the size of the aperture is given, then, as I said, my theta minimum, which is equal to D, the smallest distance to be resolved, divided by this L, should equal to 1.22 lambda over A. Lambda and lambda is given, A is already calculated, D is also given in the question, so that I can quickly get my D minimum is 122 micrometer. So why I say this question is difficult? Because if you directly apply, this resolution equation, you will be able to find that A, you don't know what it is. Normally, the question will give you the diameter or width of the, for example, that's imaging aperture. But this one does not give. You have to use the diffraction equation to calculate the corresponding diameter or width. Okay, diameter or width, and then in order to get the final answer. Then, if you do in this way, of course, you will be awarded 4 marks because this is what the original solution provided. But do you say there is any problem? Do you say there is any problem? So now let me remind you. So all in this, I comment this A. When I do diffraction, I call this A is width or diameter. I always said, okay, this is for thin film diffraction. A times sine theta equal to M times lambda. That is a diffraction equation for a slit aperture, for thin film, okay? But then this equation is for diameter. So the problem of this solution is actually in the diffraction, it considers the circular aperture as a slit line. But then in the corresponding diffraction resolution part, it still uses the circular aperture. So this is what the solution is wrong. Because if you pass light through a hole or through any circular aperture, such as a lens or a mirror, its dark fringe position is not given by this equation. A times sine theta is not equal to lambda. M times lambda. A times sine theta should equal to the 0 point of Bessel function. Okay, should equal to the 0 point of Bessel function. Of course, this is go beyond of our class. But if you want to solve that, okay, so this is not required, but I just want to let you know, add more to let you know. If you really have light passing through the hole, the position of the first and the dark fringe should be found in this way. The first should be equal to 1.22 times lambda, because the first bright fringe happens at 1.2 times lambda. This is why In the resolution part, we have 1.22 times lambda over V. This 1.22 is exactly this one. So the second factor should appear at the second zero point of this function, so which is 2.23 times lambda. Then in this case, if you do in this way, you will find that your diameter, now this is now diameter, okay? Because this apply for a whole aperture, circular aperture. So now A is diameter. Previously, my A is width, because this is a slit aperture. Now my A is my diameter, then you calculate your diameter in this way, you find that it's a little bit different from the previous one. Then you will be able to find the smallest distance you will be able to resolve is 120 micrometer, 120 micrometer. So it's actually smaller than the original one, okay? So this is actually the right solution. So this is why I said, okay, this question may have little chance to be tested. First, it's difficult, and also second, its solution is not exactly correct. But in the final examination, if it was tested, you still follow this way. First, assume it's a slit aperture because this is what we learned. The other circular aperture deflection, we have a lot of them, okay, in our course. But you have to bear in mind, light passes through a hole and the light passes through a slit. They are different, totally different. Okay. So yeah, any question? So if no question, let's look at the magnetic. Okay. So maybe I will talk about two right-hand rules, and then we will take a 10-minute break, and then continue for the second part. Okay. So for magnetism, because we have learned many right-hand rules, let me remind you what are the 5 right-hand rules. We have 2 right-hand rules for magnetic forces, 2 right-hand rules for magnetic sources, 1 right-hand rules for the motional EMF, 2 plus 2 plus 1, 5 right-hand rules. So if you have magnetic force, which means as long as force is involved, we always use our 3 finger. The first 2 right-hand rules, the first one is magnetic force acting on a moving charge. Index finger Q times V. Middle finger, direction of the magnetic field. Then our thumb is a force. So for the second right-hand rules, middle finger and the thumb remain unchanged. So which means thumb is still the force, middle finger is still magnetic field. Now this QV will become I. Okay. So that's the second right-hand rule is okay because this is always a direction of the current flow. But the first equation, okay, then the direction of QV. So depending on your Q are positive or negative, my index finger should either point to the direction of V or opposite to the direction of V. For positive charge, index finger point to the direction of V. Negative charge point opposite to the direction of V. This is what we have to bear in mind. Okay, the 2 right-hand rules for force. Then the 2 right-hand rules for the magnetic source. Okay, for the magnetic source, I will talk about later. Okay, I will talk about that later. Okay, so now it should apply, with our current, with our thumb as a current, 4 finger enclose the direction of the magnetic field. Okay, so that is the other 2 right-hand rules, which I will talk about later. Okay, so here we have a proton with a velocity. Okay, we have a proton with a velocity equal to 1 times 10 to the 8 meter. Okay, it enters the magnetic field. Okay, it enters the magnetic field. So the magnetic field only exists in a certain, a region of the space, in a certain region of the space. So it enters the uniform magnetic field, along x direction with a magnitude given by here, and then leave this field with another velocity v2, which is along minus y direction. Okay, as illustrated in this figure. I want you to calculate the direction of the magnetic field, radius of curvature, distance traveled by the proton in the field, and the time spent by the proton. Okay, so let's look at this four parts one by one. So first, the direction of the magnetic field. Here we have a proton. Right? So that for proton, QV is along the direction of QV is along the direction of the wave. Okay, QV is exactly on the direction of wave. So which means our index finger should just point here to the positive x direction. If the index finger point to point x direction, can you tell me when light is at this position, what will be the direction of the magnetic force? Magnetic force along which direction? Z, y, minus y, or minus z. Look at the coordinate. When my particle is located here, which should be the direction of the magnetic force? Which? You know, particle doing circular motion, so it should always along the radius. The force is along the radius because it's central pair force. Now the particle is doing circular motion in the xy plane, not xz, it's xy plane, okay? Then my magnetic force here should along which direction? From the trajectory here. Very good, should minus y direction. So which means my thumb should point to minus y, this direction. Index finger is QV. Index finger is QV, you know, should point in this direction. Then our middle finger has no choice, can only be point to the top. This is the right hand rule we apply. Or you can also apply your right hand rule at the position of V2. Now V2 is along minus y. Can you tell me my force along which direction? Force. So now at this position. So which is the direction of the radius? Circular motion radius. Minus x, very good. So which unit now is along minus x. My middle finger now should point along minus x, point into the page. My middle finger or index finger QV should point along minus y direction. Again, or middle finger should point to the top. Okay, so no matter for at the position of V1 or V2, I should have the direction of my magnetic field along point to the top along positive z direction. This is what you should copy down here. It should be point direct to the top along positive z direction. Then the second part is calculate the radius of curvature. V is given, QB is given. Of course, the radius of curvature is MV divided by QB. Directly use the formula, you can get about 1.04 in meter. This is radius of curvature. Now it asks you the distance traveled. Then this is very interesting. The particle is doing circular motion, but because the magnetic field does not fill the whole space, so the particle only complete a certain trajectory and leave the magnetic field. If originally it instead along x, leaves the field along y direction, how many portions of the circle the particle complete? One half, 1/4, or 1/8 of the whole circle? Very good, 1/4. So here I should talk about more. So in case some of you still does not follow what I'm talking about, I want to draw something. This is also what some of the previous students feel confused. So that you can see my plot, right? So which means what I am now drawing is directly this x, y plane. Okay, I'm not looking at this. I'm not looking at this three-dimensional. I'm just looking at the x, y plane. The question tells us that the electron just enter along minus. Let me see. So yeah, it's along minus x direction. Oh, sorry. So which means now I am so this x. Now this should be y. The electron enters at the minus x direction this way, then doing circular motion. Then it leaves when it becomes velocity becomes along minus y direction, then it will leave the magnetic field, which means the magnetic field only in this only in this slab region. So once it becomes minus y, it will leave the magnetic field, no longer complete circular motion. So at this position, the electron enters here and leaves the magnetic field. So as you can see here, when it direction changes from x to y, it just complete 1/4 of the whole circle. So if the question tells you, okay, the electron leaves the magnetic field just opposite to the original velocity. For example, it enters with a velocity positive x, leaves without negative x, leaves without notice, still on x, but positive x. So it will directly change direction, which means it can be a half circle. But if it just changes from x to y, it's 1/4, 1/4 of the whole circle. Okay, so this is something you have to bear in mind. Some important things here. So that because it's 1/4 of the circle, okay, it's 1/4. So my corresponding theta is pi divided by 2. Because 2 pi r is my circle. 2 pi r divided by 4 is, pi r divided by 2. So in this case, I have 1.6 meter distance traveled. So the time traveled, we have, two different methods to calculate the time traveled. Both you can use either of them. You will be awarded 4 marks. So first is to calculate because it's 1/4 of the circle. So that to complete 1/4 of the circle, I just need to 1/4 of the period. So period is 2 pi m divided by qb. So 1/4 of the period is pi m divided by 2 qb. So here I get about 11.4 nanoseconds. Or you just use this easily as the whole distance traveled divided by the corresponding velocity, you get exactly the same answer. Okay? So this is how the 4 part should be solved. So if you have a question, raise your hand. Otherwise, I will continue. And one of the important things for the magnetic part is to do particle filter. Okay, to do this particle filter. So that for particle filter, it says, okay, we have both electric and magnetic field. Okay, if you want a particle to passing through this particle filter, it needs the magnetic field to cancel out the electric field. Okay, so only for a certain velocity, its magnetic force and the electric force can cancel out each other, so that the particle can get through. So this is what we call for particle filter. So here I will have a conclusion highlight for you. So for particle filter, okay. So here we have a particle filter which is a velocity selector. Okay, this question said it's a velocity selector. It's the corresponding electric field is given by this value. So it's directly from bottom to the top. So then we have another magnetic field that is directly perpendicular to our page, but whether it's into the page or out of the page, we don't know. Then we have an electron. Now it's an electron enters this particle filter with a velocity v. First, I want you to determine the magnetic field, whether it's out of the page or into the page. Second, I want you to find the magnitude of the magnetic field B that will ensure the electron with a kinetic energy 300 eV to pass through the velocity filter. It will not be deflected. So 2 parts. So normally for the particle filter is for us to apply the right-hand rules to determine the direction of the magnetic field, or okay, it will ask you to find out either what is the velocity, or what is the magnetic field, or what is the electric field. Because for a particle filter, the velocity to be filled out is directly related with the magnetic field and the electric field. Okay, so which means given only 2 parameters out of velocity, magnetic field, and the electric field, we will be able to use a certain relationship to find out the unknown one. So I will talk about this when we complete the first part. So this is the configuration we are looking at. F equal to E plus V cross B. So what we want is, E plus V cross B equal to 0. So which means my V cross B should exactly opposite to E. The question tells us that the E is point to the top. So if I want my total force to be 0, magnetic field cancel out the electric field, I want my V cross B opposite to E, right? So for particle filter, you don't have to worry about its electron or proton, positive or negative charge. We always want V cross B cancel out of E. So now, if my E is point to the top right, to the top direction, my V cross B should point to the bottom. So which means my index finger V middle finger magnetic field should point now to the bottom. Okay, because V cross B, so we use our right hand VBE. Then we don't have to worry about the Q in this case. Because no matter is for positive and negative charge, okay, we have V cross B opposite to E everywhere. Okay, so that this Q doesn't matter. So in this case, I should allow, I said for particle filter, this is only for particle filter. What I'm doing is not looking at the direction of the magnetic force. Okay, I'm looking at the direction of V cross B. You should be opposite to B. Once V cross B opposite to B, then the electric force and the magnetic force can cancel out each other. Am I clear? Okay. Now it gives you V cross B top to the bottom, so which means my thumb should point to the bottom, right? My index finger is still V. It should point to the right, so that my middle finger in this case should point out of the page. This is the right way, okay? This is the right way for us to apply our right hand, okay? Thumb point to the bottom, index finger point to the right, middle finger point out of the page. So that here we should come now, okay? According to our right hand, my magnetic field should be directly perpendicular but out of the page. Then this is always okay. E plus V cross B equal to 0. This is in the vector form. So in the scalar form, it's always my V equal to E divided by B. Okay. So in the scalar form, is the magnitude of E equal to the velocity times the magnitude of B. That is what I'm doing. This is an important conclusion. I hope every one of you will remember this. This formula will not be provided in your formula sheet. E equal to VB will not be provided in your formula sheet. Remember it, directly apply it, you will still be awarded a 4 mark. Okay? Important thing, let me repeat. E equal to VB is what you have to remember. Okay? Then the question already tell us what is my E. Want to find out my B, I need to know the velocity. Question give us the kinetic energy, so that we use square root 2 times the kinetic energy divided by m, I can get the velocity. So here 300 EV, to do the calculation, we have to first change it to joule. By times the electron charge, 1.6 times 10 to the minus 19. Don't forget about this part, so that you get the velocity V. Okay. Also, if you want to check whether your velocity is realistic, okay, you have to say whether this is smaller than the velocity of light. Then if in your calculation you find the velocity of the electron is somehow larger than 3 times 10 to the 8 meter per second, which means you definitely make something wrong in your calculation. Because the electron cannot travel at a speed larger than the light's velocity. Okay, so it should always be smaller than 3 times 10 to the 8 meter per second. Then get V, my E divided by V will give us my velocity. Will give me the corresponding magnetic field. Okay, corresponding magnetic field. Okay, so then with this, I will talk about the other 2 right-hand rules, in the second part, then followed by some other questions on quantum physics. So that is already about 3 p.m. So that for those of students who have something to do, maybe you can leave. We will now take about 10 minutes part. Come back at 3.5 to continue the second part. Okay. Okay, let's take a break.
Can you go back the slides? Okay, one more slide now. Yes, why m doesn't start at 0?
Like, because if m equals to 0, lambda is active. But so if m starts as a because if I have m, for example, if this is 20 minus half lambda, then m can start as 0.
Okay.
Because it's m1 plus 0.5. You need to check whether this makes sense. M starts with 0, lambda is negative, that cannot happen.
Okay.
But if this is minus lambda and then you plus this equation, and then it's m1 plus 0.5, and then m can start with 0.
Okay.
M can start with 0. So mathematically, the m can start with 0. But m start with 0, you get a lambda which is negative. That is not make sense.
Okay.
Does not make sense. So in this case, m star is 1.
So it's depending which formula you use for this one. So if it's
yeah, which formula to use? If it's minus, somehow you get, and then in the denominator is m1 plus 0.5, and then it can start with 0.
okay. Okay. Then another one, right? The 600 bright fringe, right? I thought doesn't the first bright fringe occur at n equals 0?
The first 100 bright fringe, this is also a very good question. You can say still. If the first start as equal to 0, you still get your number equal to negative.
Oh, okay.
So m also start as 1 because it's m minus 1 over 2. Okay. So m can only start with 1 and to 600. But again, if this is m plus 1/2, and then it starts at 0.
Okay. So
and the 600 is should be 599 plus 1. Yes.
Okay.
But anyway, it's always 599.5. As long as the bottom here is 599 plus 5 is okay.
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 Can. Okay.
Okay.
Yep.
Good.
Thank you.
No problem.
I'm a big fan of you. Thank you. Monday你的管理啊，因为你会在那边里面。Young boy. My first class at then after that my next class to the team. electron dancing around and the blue font. Only other cameras are busy.
One of them. You don't know shit, you want to do the thing they give you. I already know trust in myself.
I start master a bit, but the DC I couldn't. First lesson I
What? No, actually, what? It's actually the. Because this has to do with visa. She said that on this visa end, right, it's all to do with VCRE. So VCRE said no.
Now she asking me to use it.
But I'm gonna push the guy.
Transmission rate and the reflection rate, right?
we talk about the group. United for the group. And then we were second. And then now they semi-final.
I think maybe
it's like, don't know how they don't know how they play. But somehow they use it.
I think it's like
technology.
I mean, I stopped watching it.
I watched this one. I think AE also everything okay, but you know that the last exam paper for like some EKT more than $1. Only the latest one, the latest one is the most latest one. That's the most relevant one. The previous one. I mean, all my else can do. For the non-ideal one, the solution also wrong. You know the solution for the non-ideal one? Not easy, it's like a fish one.
Okay, hello, ladies and gents. Time for us to back Yes, time for us to back to our class to start the second part. So as I said, for this part, I will continue with the magnetic and talk about, the three most important concepts in quantum physics. Okay, so now previously I told you two rules about the two random rules for magnetic forces. Now we have, two right-hand rule for magnetic source. Okay, so magnetic source is okay. We can use current to generate field, okay, generate a field. So in this case, no force is involved. As long as we don't have force, we only have current to generate magnetic field. Okay, this is right-hand rules we apply. Okay, so for example, for solenoid, for a line current or some is the direction of magnetic field. Four finger enclose the direction of magnetic. Some is the direction of current flow. Four finger is the direction of the magnetic field. Okay, so if I have a current, okay, so this is, for example, Biot-Savart law, when we have a line current here, or four finger enclose the field. Thumb is the direction for the current flow. So in this case, our thumb pointing to this direction. So at the top, we have magnetic field out of the page, bottom magnetic field into the page. Okay, into the page. So the same also apply here. If I have a line current running from the top, and then we view from the top, we get this clockwise magnetic field. Then in this case, we get this counterclockwise magnetic field if we view from the top. Okay, so this is right-hand rules for a line current. Okay, so right-hand rule 3 and right-hand rule 4. Okay, both of them you might understand for Ampere's law and Biot-Savart law. Okay, and the final right-hand rules is for motional EMF. When we move a conducting wire, in a magnetic field, we will create a voltage between its two ends. The current will flow from, so the electron from downward, but the current is from positive to negative ends, okay, to a Hahn potential. Okay, then the fifth right-hand rules tell you what will be the direction of current flow in motion EMF. So V cross V, index finger is V, middle finger is B, with our thumb point to the direction of the current flow or the higher potential end. So in this case, we apply this way. V, B are the direction of the current flow in the voltage in the EMF. Okay, in the EMF. This shows the direction of the electron flow. Electron flow, current flow in the different direction of the electron. So that's the current flow to the positive end. Okay. So these are the four right-hand rules. Now, yes, any question? Okay. So then let's look at some question here. So again, this is about 6 years ago. So here we have two non-parallel conductors. They are directed out of the page as shown in this figure, below. So it carries a current I1 equal to 2, I2 equal to 5 ampere. I1 equal to 2, I2 equal to 5 ampere. These two conductors are perpendicular and are located are perpendicular to the page, and then are located at 7.5 centimeters away from this x-axis, as shown in this figure. Then I want you to determine the magnetic field's magnitude and direction at this point P. Okay, this point P from 50 centimeters to both is on x-axis. Okay, it forms 50 centimeters, to both currents. So which means this point P and the position of the two wires form an equidistant triangle. Okay, for an equidistant triangle. So which means each angle here is 60 degrees, and half angle with respect to x here, this should be 30 degrees. This should be 30 degrees. So now this want you to to vector summation. So that we have to first, of course, this point P experiences two magnetic fields generated by I1 and I2 respectively. So for I1, B1 is equal to mu naught I divided by 2 pi. divided by 2 pi. I1 is given, R is given. Y is this 0.15 meter because it's 15 centimeter, 0.5 meter. So I can get the magnitude of B1. Because B is a vector, we also need to determine its direction. So in this case, it should point up when we apply our right hand, okay, with our thumb point out of the page. Then magnetic field should now in this counterclockwise direction. Counterclockwise direction. It should be perpendicular to this radius. Okay, perpendicular to this radius. So that it can only be along the top right direction. Clockwise, perpendicular to the radius. So that it's along the top right direction. This is 30 centimeters, so this angle is 60 centimeters, okay, 60 centimeters. So top right direction, which means X and the Y components are both positive. So X component is positive I times cosine 60 degree. Y component is positive J times sine 60 degree. So that I can write B1 in the vector form. Now, I want you to follow the same procedure to calculate my B2. My B2 should along which direction? Top left, top right, bottom left, or bottom right? Very good. Top left. Again, out of the page, which means it's still counterclockwise. Perpendicular to this radius, which means it can only along the top left direction. Okay, top left direction. So that B2, okay, B2 mu naught I2 divided by 2 pi r, I can get the magnitude of B2. Then its X component, okay, should be minus I times cosine 60 or I times cosine 180. Cosine 190, oh, sorry, 120. Cosine 120 is minus I times cosine 60, okay, so it's minus sign. So Y component is still positive. No matter sine 120 or sine 60, they are the same. So that X component negative, Y component positive. So that when you sum these two values together, okay, X plus X, Y plus Y, then you get the final answer in this way. Okay. Then we have another one. So I think this is also a very, very good question. I think many students didn't even know how to start with this. This is also I would like to talk about. So also about 6 years ago, exactly in semester 2, okay? So here we have two long straight wire, Y line along X direction, carries a current I, so it's flowing in positive X direction. The other straight wire line along positive Y axis, okay, carry a current I divided by 3, then it flows a positive Y direction. Then I want you to determine the trajectory of points on the XY plane where the net magnetic field is there. The field is there. Okay. If we horizontal wire, if we say the magnetic field generated by the horizontal wire is given by this blue color. Okay, we call it BI. Magnetic field generated by the vertical wire, we call it BI over 3. Okay, we call it BI over 3. Then, if I want this field to cancel out each other, what we need is these two fields should be opposite in direction under the standing magnitude. So we first need to find out, the 4 quadrants. In which quadrant the two magnetic fields, BI and BI over 3 are opposite in direction. Okay, are opposite in direction. Let's first apply our right hand for the horizontal wire. So which means in first and second quadrant, above the horizontal axis, I have my field BI out of the page. At the bottom, BI should point into the page. Okay, this is for this blue color BI. Then if you look at BI over 3, then our right hand should be applied this way. So on the left, quadrant 2 and quadrant 3, we have this dot red color BI over 3 is out of the page. On the right, first and fourth quadrant is into the page. Then from this graph, can you tell me in which two quadrants the two magnetic fields are opposite in direction? in which two quadrants, the two magnetic fields are opposite in direction. Yes, should be top right and bottom left. That is quadrant 1 and quadrant 3, right? Then, which means in these two quadrants, if we can find out the corresponding points, BI and BI over 3, they are the scattering magnitude. Then, along that points, we should have the total field is there. Then, what we do next is to find out the corresponding magnitude for BI and BI over 3. For BI and BI over 3. Okay, so first let's look at for this BI horizontal wire. Can you tell me what is this? So if, for example, here I have a point here, what is the distance between these points to I? Then if I have a point, for example, located here, what is the corresponding radius from that point to my horizontal axis? What should be the magnitude, the distance? Because we need to apply mu naught I divided by 2 pi r, right? Mu naught I divided by 2 pi r. Now what I am asking, for any point, the distance from that point to this horizontal line, what are the distance? It should be y, right? For example, this coordinate this coordinate. If this coordinate has this points have a coordinate x and y, then y is the distance measured from that point to the horizontal axis, right? So which means for BI, I should replace my r by y. Mu naught I divided by 2 pi I. Then how about the distance from the same point to the vertical axis? What's that radius or what's that distance? I have a point, the x, y coordinate are x and y. What's the distance from this point to my vertical axis? Yes, very good. That should be x. So that we should use 2 pi mu naught I divided by 2 pi x. Now I should be updated as a current carried by this vertical wire, so it's I over 3. As I said, once these two are the same in magnitude, and they are located in the top right and the bottom left quadrant. On the bottom left quadrant, I should have the total magnetic field equal to 0. So that you equal these two together, cancel out mu naught I and 2 pi, you will be found the corresponding coordinate is y equal to 3x. This is actually this dashed line. So which means if we place the current in this way, along the dashed line, I will have my total magnetic field equal to 0. Okay, so now if in the question I said, okay, this minus I over 3 or I over 4 is now running down, then you need to find out what are the corresponding position. Okay, you need to find out what is the corresponding position. So that in this way, it should be something in the second and the fourth quadrant. Okay, something in the first and fourth quadrant, and then point in the second quadrant. Okay, you should have the point in the second quadrant because their x in this quadrant. Okay, because its x coordinate are negative, so that you should have a minus x here. Y coordinate are positive. Okay, so it's still 2 pi y, but this should be minus mu naught I divided by 2 pi x because now x is negative. The corresponding radius should be minus x. So that in this case, you should get y equal to minus 3x, something like that. So that is a dashed line in the second and fourth quadrant. Okay, so this is the way to solve this question. Then the Faraday's law. So for Faraday's law, so I think it's quite easy. So just says that EMF is induced by the time rate of change of the magnetic flux. Time rate change of the magnetic flux. So we have a past examination paper question, but I have already talked about this question in order to tutorial about Faraday's law, so that I will not spend time to go through it. If you want to know the solution, you just refer to my previous slides or my previous recording about this, because this question has really been talked about. Okay, Faraday's law. So I will quickly go through it. Okay, it just show you how the magnetic field is changing with time want you to find out at the certain time where the induced EMF is 0.1 in volts, and then what will happen if it's another at 60 degree? You can refer to my previous solution, okay? And also here the solution is provided here. So that what I will focus on here is because for Faraday's law there is one important equation, so which means the EMF is just equal to n times the first direction of the flux. So that will be quite easy. So for inductance, so here you should remember actually we have about two important formula, or you can say we have another one, so which is half Li squared, which is an energy squared inductance. But the two most important formula is first the relationship between the inductance, current, and the phi. Okay, so L times I always equal to n phi. So which means if the question is telling you self-inductance, tells you the current and the inductance, then you will be able to know how to use L and I to get phi. Or if give you the total flux and the current, then n times I divided by current, that will give me the L. Okay, so again, you need to remember how to use L I equal to n phi, this formula. Give you either two parameters out of inductance L, current I, and phi, you will be able to use this formula to calculate the third amount. Okay, so this is the first equations for the inductance relationship between Li and phi. The second one is the relationship between epsilon, so which is my voltage, L and di over d phi. Okay, di over d phi. So in this case, my epsilon equal to L times di over d phi. So the relationship between the EMF induced voltage, inductance, and the first derivative of di over dt. Okay, this is the voltage. The second equation. So we have another equation now. Okay, what are the energies stored in the inductor? So that is half Li squared. Okay, half Li squared. The third important formula. Now let's look at. I think here we have look at one solution. Okay, one question about 7 years ago. So which means inductance sometimes may also be tested. But if you say that question, don't be afraid, because it will normally just test you apply these three formulas. Either Li equal to n phi, or epsilon voltage equal to L di over dt, or total energy half Li squared. So now let's look at this one. Here we have an ideal solenoid 310, so which means my n equal to 3, and the cross-section area A equal to 1 centimeter square. It generates an EMF. Now epsilon EMF is given 100 microvolts. When the current changing at a rate, okay, so it generates a 100 microvolt, EMF. When the current is changing at a rate of 50 amperes per second, so di over dt now is given, okay? Di over dt is given, epsilon is given, which means I can directly use the second equation here, epsilon di over dt to get L, because now my epsilon and di over dt is given, okay? So that it wants us to determine the solenoid. As I said, epsilon di over dt is given, I can directly determine the L. Then I ask you at a certain instant, if the current is 5 ampere, what should be the magnetic flux? Then this is Li equal to n phi. If you get L times I should be equal to 10 phi. Then L times I divided by n is my flux, and then the corresponding magnetic field through the solenoid. So this question looks like we have a lot of information, right? But as you can see, it can be solved very, very easily. Carry 30 marks, okay, 30 marks, a lot, no? But you can see each part, you can just solve it with one single equation. The first one is the magnitude of the EMF equal to L times di over dt. Voltage is given, di over dt is given, so that my L should directly equal to the voltage divided by the time rate of change for the current. So we get 2 microhenry. Okay, directly apply epsilon equal to L di over dt, you can get the L. Then the second part said that if my I is 5 ampere, what should be the flux? Then it tells you apply Li equal to n times 5. Okay, we only have these three formulas, okay, for inductance. We only have three formulas for the inductance. We just go to your formula sheet, identify the right formula to apply it, and problem solved. So that's if you found the right formula for this case, phi equal to Li over N, then flux is given. So if magnetic flux is given, how can we get the field? Very good. Phi equal to B times A, right? Area is given, so which means my B should equal to phi divided by the area. Then I get the magnetic field. Okay? Although 30 marks, but you can say each part only one equation. Also, the standard equation you can find in your homework sheet. You can directly solve it. So I hope if you see this question, maybe it's how to say, looks a little bit weird or unfamiliar to you, but don't be afraid. Normally, you just identify, okay, which part this question is asking you. As I said, for inductance, only these three important formulas. So if it's Faraday, so it's even easier because we only have an equal to n times d phi over dt. So that can be solved even more quickly. Okay.
For the EMF, right, why do you take absolute? Like, where's the negative? In the formula is negative L.
Oh, the negative L is that is for the solenoid. So for the solenoid, so to find out, so which means when the current increasing, the induced MF will try to prevent the current from increasing. But when you solve that mathematically, it gives you what is first the inductance has to be positive. So when we do mathematics, we normally take the absolute value, using the absolute value of the EMF divided by the absolute value of di over dt. Then we can get L, because L cannot be negative. Okay. So the quantum physics, as I said, for quantum physics, especially when you don't have time to prepare, just first look at the three important parts: photoelectric effect, hydrogen atom, as well as the quantum wave. So first, let's look at this hydrogen atom. For hydrogen atom. So for hydrogen atom, here we have what you have to remember is this Born's formula and the Born's assumption. So for Born's assumption, so what hydrogen atom, what the quantum physics tells you, for an electron circling the atom, its velocity and the radius of the orbit of the electron orbit is quantized. It cannot be any value. Okay, classical physics tell us it can be any value, but the quantum physics tell us that the electron circling the atom, its orbit is always quantized. It also quantized. And then how the orbit and the velocity of the electron quantized is given by Born's assumption 1 and 2. So first one is the central pair force given by the Coulomb attraction. The second one is the angular moment is quantized, which means my mv times r equal to nh divided by 2 pi. So that if this question asks you to calculate what are the quantized radius or quantized velocity or quantized the wavelength of the electron. So anything related with the electron, you need to apply Born's first and fourth assumption. So use these two formulas. So that these two formulas are related with the property of the electron. So similar to our quiz, okay, similar to our assignment. In our assignment, question 4, right, it asks you what are the Broglie wavelengths of the electron in orbit. This is the two formulas you apply. Once you apply this formula, you find out the way, then h divided by mv, that will give us the Broglie wavelengths. Okay. So what we do here is to find out the V. So this understanding. So as let me highlight, for electron, if the question asks you for anything about the electron, like as its speed, its radius, we use these two formulas. Then the other two formulas is related with photon. Okay. So if you want to find out what are the wavelengths or frequency of the emitted photon, you have to start with the energy of the electron at different orbits. Find out the corresponding energy difference using the energy difference between the initial and final states. Set that equal to h divided by lambda or h times f, you can get the frequency or the wavelength of that emitted or absorbed photon. Okay, so hydrogen atom can only test in this two ways. Either ask you to find out the property of the electron like its orbit or velocity, then you use this formula and this one. Or ask you to determine the emitted photon wavelength or frequency, then you use this formula and this formula. Okay, this is normally hydrogen atom will be hesitate. Okay, so then let's look at some question. Okay, 4 years ago, here is the emission spectrum of hydrogen atom in visible light shows 4 sharp colorful lines at these 3 wavelengths. Okay, at these 3 wavelengths. Then I want you to explain the origin of the emission spectrum using Born's model, and then determine the energy between the corresponding level, and comment on whether the difference between the energy level agreeing with the energy of the emitted photon. Agreeing with the energy of the emitted photon. So for this one, you have to remember something. So hydrogen atom is emission in the visual spectrum is not the results from the translation of the electron from the excited state back into the ground state. According to the lecture, this is not, because transition from excited state to the ground state that always emitted in the ultraviolet fixed regime. That always emit very high frequency, short wavelength light. The fourth spectrum is the visible one is due to the transition back to n equal to 2 excited state. Transition back to the first excited state, not to the grounded one. So this is what Lam's video comment on. Okay, so which means this 4 lines corresponds to transition from n equal to 2, 4, 5, 6 back to n equal to 2. So not n equal to 1, n equal to 1 is a ground state, but here is transition back to n equal to 2. So that, for example, the longest wavelength corresponds to transition from E3 to E2. And the shortest wavelength corresponds to the transition of electron from E6 to E2. Okay, so this is what you have to comment on. So that we should look at is this one. Okay, this 4 lines, your explanation. So the other one, I don't think you need to write. As long as we see this 4, you will get 4 marks for the first part. 4 marks for the first mark. For the first mark, as I said, the first one, worth 4 marks. Okay, worth 4 marks. So if you have E2 over E3, E4, then each line over 1 mark. Each line over 1 mark. Okay. Then what you have to do is to calculate. Okay, what are the energy difference between E3 and E2, and then see whether that agreeing with HC divided by this lambda. Then we redo that for E4 to E2, E5 to E2, and E6 to E2. So that using hydrogen energy level En equal to this guy, so we need to check the validity of this formula. So that for the transition from E3 to E2, then we use this formula, substitute N equal to 2 and 3 into this formula, found out the difference. We found this is about 1.89 eV. Then corresponding HC over lambda is also 1.9 eV, so which means they are perfectly equal to each other. So that for this line, the theory is correct. Then we check for the other 3 wavelengths, E4 to E3, then this is 2.55 eV. Then corresponding HC over this lambda is about 2.56 eV. So also more or less agree, less than 1% difference, which means still agree quite well. So for this wavelengths, both are 2.86 eV, so also agree. So the last one is 3.02 eV, the other is 3.03 eV, also less than 1% difference. So which means they agree quite well, which means this theory is correct. This is how you should provide a solution for this question. Okay. Then photoelectric effect. So why I talk about photoelectric field, behind hydrogen atom, because sometimes the photoelectric effect and hydrogen atom will be combined in the same question. So this is the question I will talk about. But before talk about the question, let me highlight for you some important formula for the photoelectric effect. So as I said, hydrogen atom we have 4 important formulas. Okay. 2 important formulas to find out what are the properties of the electron, for example, the orbit and the velocity. Other important formula to find out what are the emitted photons energy. So for photoelectric effect, we have also two important formula. The first one is the kinetic energy of the photoelectron. Kmax is the kinetic energy of emitted photoelectron. That is to be equal to hf minus phi. H times F is the incident photon's energy, minus phi is the work function, different material, different work function. Once my HF is larger than phi, I can have my photoelectron emitted from the metal. Okay, so this is what we call the photoelectric effect. So an important thing is when the Kmax equals 0, that gives you the minimum frequency that needs the minimum frequency that needs the photoelectron effect to happen. So that frequency is defined as the cutoff frequency, phi divided by h. Okay, when Kmax equals 0, phi divided by h will give us a cutoff frequency. This is what we mean cutoff frequency. The other thing is the kinetic energy, because the electron emitted from this source plate cannot be directly measured. In order to measure it, we need to put it in the potential, and then find out how large the photo current is generated at the collecting plate. So we assume the collecting plate, electron at the collecting plate as K infinity, because normally we think the two plates are far apart from each other. So this K infinity should equal to the emitted photon's kinetic energy plus its potential energy. The electron has a minus charge, so it's minus E times V. V is the difference between the collecting and the incident plate. It's also the potential between infinity and the plate, because we said infinity normally the potential equal to 0. Okay, then the kinetic energy we collect at the collecting plate is equal to Kmax plus minus E times V. Okay, so this is by conservation of energy. Then this will give us a stopping potential is when at the collecting plate we can just stop the photoelectron. So we use this minus EVS to cancel out the Kmax. So that the stopping potential is defined as Kmax just equal to E times Vs, the stopping potential. Okay, so these are the two important formulas for photoelectric effect, and its exchange definition about the cutoff frequency and the stopping potential is exactly given by these two important formulas. Okay, now, okay, you can see this question worth 25 marks, I would say. It was 25 marks, just the test the combination between hydrogen and photoelectric effect. Okay, so here we have a metal illuminated with 200 nanometer, illuminated with 200 nanometer wavelength light. The work function of metal is 3 eV, and its electrical potential is 5 volts lower than point at infinity. So which means now my V here should be minus 5. Because if it's 5 higher, so which is positive, lower infinity, potential is there. If it's 5 volt lower, which means Vs equal to 5, minus 5. So you can say, you set Vs equal to minus 5, minus sometimes a minus will become positive. So which means now the minus potential is used to accelerate the electron. Positive Vs is used to deaccelerate the electron. Okay. Now, actually, I can make the electron moving faster. Okay. So as I said, work function is given. Clearly, you can say, okay, definitely this will test me about the photoelectric effect. This is two important formula right now, so you will be awarded a lot of mark now. So that first, I want you to determine the emitted kinetic energy of the photoelectron. Then the corresponding de Broglie wavelengths collect at infinity. And then I want you to comment out whether this photoelectron can excite ground state hydrogen atom placed at infinity. So let's look at this two parts one by one. The first part, 50 marks. As you can see, this 50 marks can be just solved by a single equation. It worth 15 marks, okay, 15 marks. Just this one. Kmax equal to HF minus phi. When you get 3.19 eV, you already get 60 mark, okay? 50 mark, okay? Very easy, right? Directly apply the formula. So the second 5 mark, okay, now we just apply the formula for the, for at infinity. At infinity, so which is my K infinity, half mv infinity squared should be equal to half mv squared. This is my Kmax plus minus EV, okay? Plus minus EV, okay? U here is equal to, -5, okay, -5. So -5 volt times E just equal to 5 eV. Originally, I found my Kmax already equal to 3.19 eV. Now the potential energy will give me another positive 5 eV. Add up these two together, I get 8.19 eV as the total energy at infinity. So in Joule is equal to this value. So that why I change it to Joule is because I need to find out the velocity of the double equivalence. The velocity of the double equivalence. Once we get the velocity, H divided by mv will give us the corresponding double equivalence. So which is about 0.428 nanometer. 0.428 nanometer. So something between ultraviolet and the X-ray, okay? So this is a double equivalence, 5 mark, okay? So this was 3 mark, this was 2 mark, double equivalence. The final thing is, okay, this one. The hydrogen atom is first at the ground state, so that the minimum energy we require to excite it to the excited state is of course from 1 to 2. So that you can see the minimum kinetic, the minimum energy we require to excite the hydrogen atom is about this 10.2 eV. 10.2 eV. So then I said, okay, the electron at infinity is only 8.19 eV. This is smaller than the minimum energy required, so that it cannot excite the hydrogen atom. This is what we have to comment here. Okay, well, this is what we have to comment here. So you have to first get this one worth 3 mark. Commonly it cannot excite. That will worth another 2 marks. Okay, so here I have something I want to highlight for you. So if I want to electron to excite the hydrogen atom, because you know electron can move at any speed, so it can give part of the energy to the hydrogen atom to excite the hydrogen atom, and then keep the rest of the kinetic energy with me. Because its velocity can increase, it can give out any portion of its kinetic energy. But now, if I am looking at a photon, for example, my photon, if the photon's voltage is for kinetic energy or its energy is 11 eV, then comment whether this 11 eV can excite the hydrogen atom from state 1 to state 2. Whether or not? No, very good. Because photon is different from electron. Electron can give any portion of its kinetic energy and keep the rest with it. Okay, but photon can only move at the speed of light. Photon can only move at the speed of light. It can only either completely absorb by the atom or doesn't absorb at all. So which means if you want your photon to excite the hydrogen atom, the photon's energy must exactly match the energy difference. If it's larger than the energy difference, not exactly match, then it cannot be absorbed by the atom. And this hydrogen atom will still remain at the ground state. This is why if you say, okay, you found your content assignment very easy. Why you only get a 90 mark? This is because of this part. In your content assignment, I think question 3 or question 2, right? 3 or question 2. So in the test, you get exactly something at 11, not exactly match. Then in that case, we think it's large than 10.2 eV. You think it can excite, and then this will detect mark. This part will be detected mark, okay? Because the correct answer is it cannot. For photon to be absorbed, exact matching is very, very important. So this part I highlight for you. Okay, so quantum physics is still okay. 19 is still close to A. But if single question is tested in the final examination, I hope everyone of you should try to write this now. Electron and photon are different. Electron, you judge whether the energy is larger than this or not, because electron you can travel at any speed. It can give any portion. As long as my electron, for example, if electron is 11 eV, then we judge whether it's large or small. Okay, if it's electron is 11 eV, yes, it can excite, because it can give 10.2 eV to the hydrogen atom. gives another 0.6 eV or 0.8 eV weightage. But the photon cannot do this way. Photon can only move at the speed of light. A single photon it cannot change its frequency, okay, or this photon is slowed down. That cannot happen. So that it can photon must be exactly matched to the potential energy difference. For electron, as long as it's larger than energy difference, and then it's possible to excite. But the photon must exactly match, okay? I added this many times, okay? Photon and electron are different, okay? So that when you doing final examination, do look at whether I use the photon to excite the hydrogen atom or electron to excite it. And then you have to think this two differently. Okay? Am I clear?
No.
No?
Yes, yes.
So which part of the if you think a lot clear, I think this is important. If you think anything not clear, just you know ask. What do you think a lot clear? Clear, okay? Good. And then last part about quantum wave. Okay, last part about quantum wave. Quantum wave is also a very important concept, you know, as in the hydrogen atom. So but what I will comment actually it's similar to hydrogen atom. It's very similar to hydrogen atom. The only difference, okay, the only difference is energy. So for this quantum wave, so let me highlight for you how it will be tested. So first, it will still be tested about what are the emitted or absorbed photons energy or photons wavelengths. So that you still find out the energy difference between two energy levels. Let that difference delta E equal to hc divided by lambda to get the emitted photon wavelengths. So this is similar to the hydrogen atom. But you know, just the energy is calculated differently. Hydrogen atom is minus, right? Hydrogen atom here is minus 30.6 divided by n squared. This is the hydrogen atom divided by n squared. While for quantum box, my E is not proportional to n squared. So this is the only difference. They are only different in the energy are calculated in different way. Okay. So another thing here is okay. Electron in the quantum box at different energy level. It's a wave function. This is what you have to remember. Okay. It's a wave function will behave differently. At n equal to 1, so it's just 1/2 of the sine function. So which means it only have one side loop. Okay. It only have one side loop. When n equal to 2, it has one positive side loop and then a negative side loop. So it has twice. Okay. So you have to change it from the top wave to the bottom wave. Okay. It has two wave function. Then n equal to 3, 1, 2, 3. Okay. So that how many quantum number n equal to 1, 2, and 3 just correspond to how many patterns here you have. N equal to 1 only one pattern. N equal to 1 and 2. But bear in mind, at the boundary of the quantum box, your wave function has to be 0, has to meet 0. Okay. From 0 to maximum 1, and then here 0, meet another 0, and then back to 0. Okay. So that here you have two patterns. N equal to 3. 0, 0, 0, 0, okay, 1, 2, and 3, 3 patterns, okay. So that's the quantum number of quantum wave just tells you how many patterns of wave you will repeat, okay. So sometimes we will ask you to draw the corresponding wave function at a certain energy level. So this is how you should do it. So for quantum box, from my experience, it can only be tested this way. Either ask you to find out the emitted photons wavelengths, or ask you to draw the profile of the electron. So the profile of the electron is just a wave function. Okay, the wave function at that corresponding energy level. So for hydrogen atom, then we can ask you to find out what is the velocity of a certain energy level. What are the for example, orbit. But for quantum box, we don't have orbits. And then the velocity is very easy, like En just equal to half mv squared. And then you will be able to get the velocity, okay? But another thing is you have to draw the wave function. Also, you have to remember in this way. The number N just correspond to how many patterns you have. Okay, clear? Good. And let's look at 3 questions. So I will go through. Here we have an electron trapped at the ground level of an infinitely deep quantum well with a width of 0.2 nanometer. With a width of 0.2 in nanometer. Then determine the ground level energy. N equal to 2 already give to you. Okay. Then after the electron absorbed the photon, it excited up to the second excited level. Okay. Second excited level is N equal to 3, not N equal to 2. Okay. First excited level is N equal to 2. Second excited level is N equal to 3. And also this question also tell you the second excited level is N equal to 3. Okay, is N equal to 3. So that you follow the N directly given in the formula. Okay. So this question 6 mark, I think every one of you should try to obtain it. So if you did anything wrong, I think there is no excuse. Okay. Because it tells you directly apply the formula. N equal to 1, you look at the equation for the quantum box energy, set N equal to 1, h squared divided by 8 ml squared, you can directly get what my E1 it is. Quite easy. Then because h and L are all given, then the corresponding energy is equal to hc divided by 3 divided by hc divided by lambda should equal to E3 minus E1. So E3 is when we update this N equal to 3, so that this becomes 9. 9 times this guy, so this is E1. Okay, so it's 3 squared minus 1 squared equal to 8. 8 times, so this is 8 times E1. So here I just write this for simplicity. You can also, get the exact value. Use HC divided by the exact value. That is also the way. So in this case, you found my lambda is about 16.5 nanometer. 16.5 nanometer. Okay. So 3 mark each. 3 mark each. Okay. So one is directly calculate the energy and then find out the energy level difference equal that to HC divided by lambda, similar to what we did in hydrogen atom, okay, to get the wavelengths. So the second part will be more difficult, but you can say still, the 25 mark are very easy to get. So here we have an electron trapped in an infinitely deep, one-dimensional quantum well with a width of 10 nanometer. I want you to determine the energy of the electron under the ground and the first excited state. First excited state again is N equal to 2. And then sketch the corresponding wave function. Sketch wave function. Then the second part is more difficult. Okay. Then I said if ask you to comment how the energy and the wave function of the electron in part A will change if this quantum well is not infinite but is finite. So normally, what does this mean? Normally, we say the quantum well, okay, this is a quantum well. Normally, when we draw this wave function, we assume this U0 is infinity. So it's an infinitely deep quantum well. So which means you say a well which is infinitely deep, and the electron will have a wave function this way. If U0 is not infinite, is not very large, and then the electron will have certain probability to travel outside the wall. So it will have a certain tail. This is also what the LAMS talks about. So this is also help you to highlight. So that first, let's look at for infinitely deep quantum well, as I said, N equal to 1 and N equal to 2, you directly substitute N into this formula. So you can get what is my E1, what is my E1, what is my E2. And then corresponding wave function N equal to 1 has 1 pattern, N equal to 2 has 2 pattern. 3 mark for this, 3 mark for this, 3 mark for 1 pattern, 4 mark for N equal to 2. Okay, so this is how the marks are constituted of. Okay, for the first part. So quite easy. I think for this 13 mark, you should all obtain. So the other 12 mark is more difficult. Because for finding the quantum well, as I said, the electron can no longer be exactly confined within the box, but has a certain probability to travel outside the wall. So if the finite quantum well, their weight remain unchanged, because the electron, their 0 point are now effective outside the wall. So it looks like the effective weight of the quantum well is large. If its effective weight is right, because now it's outside the wall, which means now it's effectively the wall where the 0 point just located outside the real boundary. So it looks like the quantum will become a little bit wider. So that for finite quantum well, its energy, okay, its energy will be, okay, its energy will now be smaller than the finite quantum well, okay, than the finite quantum well, or than the infinite quantum well, because now my effective weight L prime of this finite quantum well become larger than L, so that the corresponding energy will decrease a little bit, okay, so that if you said that the energy will be smaller than En, that will give you 6 mark. Okay, if you said, okay, the effective weight is enough, 3 mark, then that leads to the conclusion energy will be smaller than equal to 6 mark. Or if you directly said, okay, because of the electron has certain tail, outside the well, so that the energy will decrease, that will directly give you 6 mark. So what we are looking at, the energy is decreasing. So if you does not get the conclusion energy decreasing, but say that, okay, the effective width of the quantum well increase, that will be about 3 marks. Okay, then you draw the plot for find the quantum well, you just modify the original solution. Okay, it has a certain tail outside the wall, and 3 mark. Okay, 3, 3, 6, 12 mark in total. Okay. Any question? Okay, so no question, then I will talk about the last one. Okay, this is the last question, so I help you go through. This is also a difficult question. Okay, so here we have a collection of electrons trapped in a one-dimensional quantum box, whose total mass is now 1.58. So now, especially for the class from student from Monday class, I think this is a question that I haven't talked about. Now I will talk about this one. Okay, so you can say this is tested about, I think, 5 years ago. Okay, 5 years ago. So that the weight of the quantum box is 1.5, which means the wave function is only non-zero within x and 1.58. With x from 0 to 1.58, I want you to show that the wave function, this guy, is the solution of the Schrödinger's equation for u equal to 0. Then I want you to express Kn as a function of A. This is the first part, worth 12 mark. Okay, first part worth 12 mark. So let's see what to do. So that already give you, I say, I want you to show what it's a solution of the Schrödinger's equation, and then want you to find out the expression for Kn, okay? So, you know, Schrödinger's fact, what is Schrödinger's function? Schrödinger's function, which means the second derivative of the phi. So especially when u equal to 0, this is the Schrödinger's function equation. Then you have to show that this equation just satisfies this one. Okay, so this is what you have to show. Okay, so that, you know, in order to show this, I need to show whether the second, so in what condition the second derivative of phi and the original wave function can satisfy this equation. So to do this, I need to differentiate the first terms. Okay, I get this Kn outside of it, it becomes cosine phi. Then differentiate the second terms, and then we have this minus, because cosine phi is minus sine phi, okay? And because of the Kn, then it's minus Kn squared times this guy, and then sine Kx. So that if I substitute this equation into the Schrödinger's equation, you will be able to say that on the left-hand side, the x-dependent part are exactly the same, just the prefactor are different. On the left-hand side, where I have the second derivative, is h bar squared Kn squared divided by 2m. While on the right-hand side, the equation is En. So in this case, you can say there is a direct relationship between E and Kn. There is a direct relationship between E and Kn. So that, you know, in this case, what we found is, okay, my E equal to h bar squared Kn squared divided by 2m. Okay, this is my Kn and E should satisfy this equation. But that's not the end. We know for the quantum, this is in a quantum box. For a quantum box is E has a, you know, determined value. So which is Hn squared divided by 8m squared. This is the most important thing here, okay? So some students did write this part, they don't know how to continue to solve that. But this is okay. You have to understand this E is exactly the energy of the quantum wave. The energy of the quantum wave is exactly h squared n squared divided by 8m squared. So that if you equal Kn to this guy, you will be directly write Kn as a function of this guy. Okay, Kn equal to nh divided by 3a h bar. H divided by h bar is 2 pi according to the definition. So you can directly say my Kn in this case is 3n pi divided by a. Okay, Kn is already expressed as a function of a. So otherwise here you can only express Kn as a function of e. How to express the Kn from the function of e to the function of a is you have to relate e to the weight of the quantum box. The weight of the quantum box L here is 1.5a, as the question indicated. So that in this way we can write my Kn as a function of a 2n pi divided by 3a. Okay, so the first 12 mark you already earned. So the second part, 6 mark. Okay, light of wavelength lambda naught illuminates the electron at the ground state of the quantum box, results in their transition to unexcited states. Given that the wave function of the electron at the excited state is this guy, I want you to find the corresponding wavelength lambda naught of the emitted electron as a function of a. So then this is also a very good question. So from what we understand in this case, okay, at the excited state, my Kn equal to 8 pi divided by 3a. 8 pi divided by 3a. Kn is a function of the quantum number n and a. So if you look at this question, okay, clearly my Kn is 8 pi divided by 3a. Compared with what we have obtained in the first equation, you can quickly show that at this excited state, the corresponding quantum number is n equal to 4. N equal to 4. So that when you apply the photon's energy equal to the energy difference between two between two energy level, so you should set one n equal to 4, the other equal to 1, so that you have this 15h squared divided by 8ma squared. So in this case, you find my lambda naught is just 6mca squared divided by 5h. Okay, 6mca. So the first thing is you need to find out, in order to find out the emitted photon wavelengths, we have to identify the emitted, the excited states, the which energy level the excited state is. From the wave function, the most important thing from the wave function is this Kn equal to 8 pi divided by 3a. You need to compare this Kn with the previous one. With the previous one, you get the quantum number n. Okay? Once this is given, maybe I can also ask you to sketch, for example, the corresponding wave function. So in this case, you have to draw 4 patterns. In that case. Then the last part, I want to know how many characteristic wavelengths can the electron emit upon relaxing back to the excited states, and then express this wavelength in terms of lambda naught. So that, as I said, important conclusion, electron at energy level n, a collection of electrons, when it transits back to the ground state, it can emit n times n minus 1 divided by 2 different wavelengths. So that in this case, it can emit in total 6 wavelengths in total. It's 4 to 1, 4 to 2, 4 to 3, 3 to 1, 3 to 2, and 2 to 1. In total 6. So that then you just substitute corresponding n. For example, for 4 to 1, we have 4 squared minus 1 squared. So that you can say it's just equal to lambda naught. Then for 4 to 2 is 4 squared minus 2 squared is equal to 5 over 4 times lambda naught. And then you do that for other 4 to 3, get corresponding energy difference, and then compare it with my original lambda naught. You will be able to write everything as a function of lambda naught in this way. Okay, so look at the math yourself. Now maybe today I will just stop here. As I said, tutorial 13 is more important. But if you have time, please also look at tutorial 14. Okay, for tutorial 14, okay, let me quickly help you go through here. So for this tutorial 14, I have some other part, okay? Other part, especially, for example, geometry optics. But that geometry optics is not multiple lengths, okay? It's not multiple lengths. It's some concept is also important, but maybe not that important as a tutorial 13. But it can also help you prepare your final examination. For example, geometry optics here I only talks about imaging, right, by lens and mirror. So if you want to look at how the refraction will be tested and how the polarization will be tested, you refer to tutorial 14 because all the solutions are provided here. So with this solution, actually, I give you a lot of solutions for pass examination methods. Nearly everyone who comes download from the library, you can have the solution in my slides. Do not trust what you get from outside because some students the solution provided the solution is wrong. You should refer to my slides. If you found some question difficult to solve and you have not found solution in my slides, let me know. Make a consultation. I can show you the right way to solve the pass examination paper. But if you get the solution from outside, when you solve it, you find your solution does not agree. So that does not necessarily mean you are wrong because in many cases, the student shows the solution, I find the solution is quite incorrect. So that if you find something that you don't understand, you don't agree with what you get from outside, do not take it as for granted that this is the right solution. You need to consult with in that case to make sure. Okay, so normally because here I already provided with you a lot of solutions to pass examination questions. When you start passing, you just refer to my slides. Okay, from all the 13 tutorial or 14 tutorial, I think we already have enough past examples for you to attend. Okay, so with this, that will be the end of the class. Also, our last tutorial class. This will be our last tutorial class. Next week is already reversing. So maybe this will be the last time I see you. So anyway, it's nice to be with you throughout the whole semester. If you have any question, remember, please you have the consultation session. Okay, this Friday and also reversion week because we don't have any class. So every week have consultation, but you have to let me know because I have some other research meeting. If you want to consult me anytime from Monday to Friday, you email me 1 day in advance. Then we can schedule a study in the next day. Okay, so for the revision will be this way. So this Friday, you come to my office or you can find me online this Friday afternoon. Okay, so next week you just let me know in advance if you want to consult. Okay, so that will be the end of the class.